Hi, I just wanted to do a quick video walking through that, finishing off that last example of doing a optimization in now more than one dimension. So I'm going to pick back up where we were with this function f of x and y, which was 4x cubed plus y cubed plus 3x squared minus minus 90x, again, minus 48y plus 15. This was our function that we used in class, and we had found that the gradient of f, remember it's a vector with two components being df, dx, df, dy, partial derivatives, was 12x squared plus 6x minus 90 for the first component. The second component was 3y squared minus 48. And we had found, by setting each of these derivatives equal to 0 in the first derivative part of this test, that this gave us a few roots at x equals, 2.5, or x equals minus 3, and then we had y equals plus or minus 4 as the other roots, which gave us 4 possible locations that we need to check. 2.5, 4, 2.5, minus 4, we had minus 3, 4, and minus 3, minus 4 as our locations where these derivatives are simultaneously 0. So the gradient is 0 at these 4 locations. So now we need to figure out that second derivative test. We have this function d of x, y, which is the second derivative with respect to x, multiplied by the second derivative with respect to y, minus the mixed partial squared. So let's calculate these. So let's take the second derivative of f with respect to x. We have the first derivative here, so then we're going to get 24x plus 6. And this minus 90 term is constant, so that'll be killed off. I want to finish off all these other derivatives though, so let's do the second order in y. Taking the next order derivative here, this 48 will go away, so we'll get 6y. And our mixed partials, we can take the y derivative of this one or the x derivative of this one, because we know those two mixed partials should be equal to each other. And you can see there's no y's here and no x's here, so both of those will be equal to 0. So we now have this function d of x, y should just be equal to this multiplied by that. So 6y times 24x plus 6. And we can determine for each one of these locations, what is the value of d? So let's go through. I'm going to label these. Let me say I'll do A, B, C. Oh, that's maybe a poor choice because then we have multiple d's. I'll just do 1, 2, 3, 4. 1, 2, 3, 4. So for root number 1, plugging in x is 2.5 and y equals 4. You can plug that into your calculator. We're going to see that that would be d of 2.54 is equal to 1584. But really all we care about is that this is positive. So we know that our 4 possible cases that we worked through in class there are three cases for if d is greater than 0. We have the possibility of a local min or a local max. So we will follow up on this one to double check it. But if d is less than 0, we know it's not going to be local min or max, or if d is exactly equal to 0, the test isn't conclusive. We might need to try something a little different to figure it out. So here we will test this root again, but first let's just check the other ones. D of 2.5 minus 4. The only thing that's going to change there is this y is going to change sign, so the value is the same, it's just we flip sign. So this is negative, and we know for sure that this is neither min or max. Our third set of roots, we would have d minus 3, 4, and plugging those things in, we will get, in this case, minus 1584. That's negative, and that's still neither min nor max. So these two are really saddle points, that we know that the second derivative in the x direction is going to have the opposite sign as second derivative in the y direction. And lastly, this fourth root, d of minus 3 minus 4, again, y is just flipping sign, which will flip this sign to now positive 1584 positive. So we have to check these two roots. What is the second derivative in those cases? We can check either one. So let's do the second derivative with respect to x. We know we have got 24x plus 6, and x is positive, so we have 24 times a positive number plus another positive number. This one will be positive, and so this will be a local minimum, because again, this is concave up in both directions. We know both directions because d was positive. We could double check, of course, that the second order derivative in y is positive. We know 6y, y is positive, so the second order in y will also be positive. So both of them are kind of concave up, and so this spot will be a local minimum. Here we can do the same type of check again. Here we're going to have, for the x partial, we'd have 24 times minus 3 plus 6, so we're going to get a very high magnitude but negative number, so a very small number below 0. Adding just 6 to it, we're still going to end up with the second order derivative being negative. So this would say a local maximum, meaning it's concave down in this direction. And of course, 6 times y, where y is minus 4, will also give us a negative second derivative in the y direction. So yes, this is a local maximum. And so this is how we should go about trying to figure out whether these things are local minima or maxima with this new version of the second derivative test. Here, we just have to be careful and double check this function d before making sure these second order derivatives are either positive or negative, because if they have opposite signs, if the second order derivative in x has the opposite sign as a second order derivative in y, then we're not going to get a minimum or a maximum, because it's going to be changing in kind of different ways in those two different directions, and at least in one direction we'll be able to either increase or decrease the function. So that is the last little bit from that chapter 4.